Welcome to Unit 9, Logarithmic Functions, Lesson 1, Understanding Logarithms. We have some definitions here. Basically, we're building off the exponential formulas we were using in the last unit, and now we're looking at the logarithms of them, which is basically just the reciprocal function. So a logarithmic function is a function in the form of y equals log cx. Notice that c is a subscript there, not a superscript, where c is greater than 0 and c cannot equal 1, so you have that asymptote available. That is the inverse of the exponential function y is equal to c to the x. So notice that there's some shared terms between these two functions. I just wanted to make a quick note on your calculator because I feel like some people might be going 2 times 2 times 2 or whatever the exponent is. You have a to the power of button on your calculator. Typically it's either x to the power of y or that little hat symbol. So if you're punching it in your calculator, depending on the calculator you have, you go 2 to the power of 3 and it will do that multiplication for you. A logarithm is an exponent in x is equal to c to the y. Y is called the logarithm to the base c of x. I know it's a lot of terminology, but don't get caught up in it. This is actually a really simple task throughout this unit, as long as you understand what these letters mean. And we also have a common logarithm, a logarithm with base 10. And I'll talk about that a little bit further down the page. So for the exponential function, y is equal to c to the x. The inverse is x is equal to c to the y. Remember, finding those inverse or reciprocal functions, we're just switching the x and y values, and you get that reflection typically over y equals x line. So the inverse is also a function and is called a logarithmic function. It's written as y is equal to log cx, where c is a positive number other than 1. So like I was saying a little bit earlier, these two formulas, the exponential and the logarithmic, are related to each other. If we look at the exponential formula first, we have c to the power of y equals x, where c is our base, y is our exponent, and x is our answer. That translates to this in the logarithmic form. We have log c of x, so c is your base, that hasn't changed. X is your answer, and y is your exponent. So for example, if we had 2 to the power of 3 equals 8, in logarithmic form it would look like this. Log of 2, that's your base. Your x is your answer, it corresponds to this number here. So 8 is equal to y. Is equal to 3. So you can easily go back and forth between these two forms. If you have the log of a function, you have your base, your exponent, and your answer right there. So sometimes you'll be left with an unknown, and you can just transfer it into exponential form and solve for your missing value. So exponential and logarithmic functions are reciprocal functions. We have some examples here of the formats that the functions could be in. So we could have y is equal to 10 to the x, f of x is equal to 10 times x is equal to 10 to the power of y, or the inverse, f to the minus 1x is equal to x over 10. There's something to note here. If the base is 10, it can be written one of two ways. You can either write it as y is equal to log 10x, or you may see it written as y equals log x. And if there's no number here in that subscript, that tells you that the base is 10, and I put a little note there for you. We just have an example. If x is equal to 100 and then y is equal to 2. And so just using these formulas up here, I've just filled in all the values for you and shown you that these are all equivalent equations. Each of them means exactly the same thing. So there's lots of different ways you can write it. In part B, evaluating logarithms, you'll be given a term and asked, oh, what does this logarithm equal to? So keep in mind from the previous page, it's equal to x. So if you're going, where did I get those x's from? It's from there. We're saying that all of these statements are equal to x, equals x, equals x. equals x. And so I won't go through all the examples. You can just pause the video and take your notes. But basically, you're just saying the log 7, 7 is your base, 49 is your answer. So 7 to the power of what equals 49? We're not super familiar with writing that statement in this format, so switch it to exponential form. 7 to the power of x equals 49. And then, of course, you just take the square root of both sides to get x equals 2. So we say the log 7 of 49 is equal to 2. Of these examples, another one I want to talk about is C. I just want to mention to you that there's no number between the log and the 0.001, so the base there would be 10, okay? And that shows up in your exponential form. The third one I want to talk about is the log 2 to the root 8 equals x. So we have this statement, 2 to the power of x equals root 8. Now, when you have a square root symbol, you can change that to a fraction in exponential form. The top number would be the power, whatever the power is that this is raised to, and then the bottom number would be the root. So if it was cube root or fourth root, it would be a 3 or a 4 there, but it's not, it's square root, so you just put a 2. So we have 8 to the power of 1/2. Now, if you recall from the last unit, what you can do is take this 8 to the power of 1/2 and change it into a common base. You'll get 2 to the power of 3, which is 8, and then times 1/2. And the last thing you need to do is just multiply these two together. 3 times 1, divide by 2. So we will say x to the power of 3 over 2. And you can't quite see it here. I'll try to draw it a little darker. Log, the final statement would look like that. Log 2 root 8 equals 3 over 2, which basically says 2 cubed square root. Now, we have some rules about the logarithm, and this will help us to understand how we need to resolve the equations when we're presented with them. So if c is greater than 0 and c cannot equal 1, then log c of 1 is equal to 0, since in exponential form c to the power of 0 equals 1. Log c of c equals 1, since in exponential form c to the 1 equals c. Anything to the power of 1 is itself. And log c of c to the power of x equals x, since in exponential form c to the x equals c to the x. This is all stuff from the last unit. It's not new content. You should already understand this basic principles about these logarithm and exponential functions. The last one, c to the power of log x is equal to x if x is greater than 0, since log c of x is equal to log c of x, because those two statements are equivalent. So you should get the same numbers in the base as well as the answer, and therefore the exponents would be identical as well. So just a note on that, the last two results, this one and this one, are sometimes called inverse properties, since logs and powers are inverse math operations that undo each other. If log c to the power x is equal to x, the log of a power with the same base equals the exponent x. In c to the power of log cx equals x, a power raised to the logarithm of a number would be the same base, and that number equals x. Now, that's a lot of words and terms, so just go through the examples and see and check your understanding. So we have some examples here. I will go through just a few of them. It's basically exactly the same as the previous example. Log 5, the 5 to the power of 3 equals x. So based on that rule up here, this one, log c to the power of x equals x. So wherever the x is, we will find it. So 5 to the power of x equals 5 to the power of 3, and therefore x equals 3. And we can say that that whole statement equals 3. Now, the long way about it in this question, you could have log 5, and then if you simplify that 5/3, it would be 125 equals x. This would also bring you to the same result. You'd get 5 to the power of x equals 125, which is, of course, 5 to the power of 3 equals 125, and x equals 3. So whichever way you come to the answer is perfectly fine. Like many other things in math, there's a ton of different ways to do the exact same problem. So you can just pause the video and take down these examples. In part C, determine an unknown in an expression in log form. Now the x is moving around, so we're just solving for an unknown value, replacing it with x. Just keep in mind those basic terms about this is log c x equals y. A couple things I wanted to remind you about in this section is that if you have a negative exponent, just keep in mind that that means 1 over 5 to the power of 3, or 1 over 125, which will give you your answer there, x. So negative exponents create a fraction. The other thing I wanted to draw your attention to is in this question, we have a fraction as our exponent. Don't get scared, it's okay. You just need to know where the numbers go. So if you have a 3 on the bottom like we do in this fraction, then that becomes the cube root of the 64. And then whatever number is here in the top of the fraction, the numerator, that becomes your power. So bottom number, denominator, determines your root. Top number determines your power. So you would take the cube root of 64, which is of course 4 times 4 times 4, 4. And then we're going to square that to give us 16 equals x. Now you can always plug these values in to see if you get that statement when you resolve this using your calculator or using your mental math. It should all add up to make sense that the cube root of 64 squared is equal to 16. In part D, graph the inverse of an exponential function. This should take you right back to the first unit where we learned how to graph inverses and reciprocal functions. So if you have f of x is equal to 3 to the power of x, you can just create some mapping points. Of course, you don't need this many points, but for demonstration's sake, it really clarifies what we're doing here. So on f of x is equal to 3 of x, we have all of these values. Notice that in the logarithmic form, all we've done is take the inverse x, y. So if you're presented with a graph and you want to find the logarithm of it, all you need to do is switch the x and y values and then plot them out. Notice the corresponding patterns for some of the information here. Remember, because we're just switching the x and y values, you will see pattern in the domain range, intercepts, and asymptotes. So I have f of x corresponding to that top graph, y equals 3 to the power of x, and then f minus 1 of x. So the domain here is x is an element of the reals. I'm just going to go down. You can see that it continues off into infinity. In f to the minus 1x, we have that vertical asymptote at x equals 0. And therefore, you won't have any negative values because we've done that reflection over that y equals x line. The range in the 3 to the power of x is restricted by that horizontal asymptote y is equal to 0, so y must be greater than that. And in the inverse, y is an element of the reals. The x-intercept, you're just reading this off the graph, or you can plug in the values. The x-intercept, if it exists, in the f of x, none. F negative 1 of x, 1, 0. Notice that in the y-intercept, it just switches places, just like the coordinate plane did further up. And then the last part, the equations of any asymptotes, just look at what line it can never hit. And for this one, it's y equals 0, and this one, it's x equals 0. So all we've done is just trade places for all those values. No new information. Sometimes you might be provided with an example that doesn't work out perfectly as a cube or square root or whatever exponent you're given. So you'll be asked to estimate the value of the logarithm. So without using technology, estimate the value of log 214 to 1 decimal place. The log is the exponent that must be applied to base 2 to obtain 14. So what we're saying is 2 to the power of what equals 14. Now we know that we go up 2, 4, 8, 16, 32, etc. 2 times 2 times 2, off into infinity. We don't have an exact value that hits 14. So this term here, 8, is 2 to the power of 3. And this term here, 2 to the power of 4, is equal to 16. That means that our exponent will lie somewhere in between those two values. Okay? Now, 14 is definitely closer to 16, so you would want to use values closer to 4 than to 3 as your decimals. So just for example's sake, I tried 3.7 first. That's approximately equal to 13. So log 2 13 equals 3.7. That's less than log 2 14. So you try 3.8, and that gives us approximately 14 with some decimal places. So we would say that log 2 14 is approximately 3.8. You can always check this with your calculator as well. The last thing that we can do is apply logarithms in real-world situations. The Richter scale for measuring earthquakes is a really good example of this. So the example says, in 1935, American seismologist, that's a person who studies earthquakes, Charles R. Richter, developed a scale formula for measuring the magnitude of earthquakes, how big they are. The magnitude m of an earthquake is defined as m is equal to log of a over AO, where a is the amplitude of the ground motion, usually in microns measured by a sensitive seismometer, and AO is the amplitude corrected for the distance to the actual earthquake. That would be expected for a standard earthquake, so it's just a reference point. Our example, in 1946, an earthquake struck Vancouver Island. It had an amplitude that was 10 to the power of 7.3 times AO, so times the reference earthquake, the standard earthquake. What was the earthquake's magnitude? Now, the AO plays a little bit of a role here in terms of it's just a term that kind of tags along and then gets canceled at the end of these problems. So don't worry about it too much. As long as you show that you're canceling it out, you should be able to get the correct answer. Now, we have m is equal to log 10 to the power of 7.3 times AO and divide by AO. We're trying to get rid of this term and solve for m. So of course, dividing by the same thing that you have will make that 1. 1 divided by 1 gives you 1. So we're left with m is equal to log 10 to the 7.3, and m is equal to 7.3, because this would be a base 10 function. So you don't see that 10 drawn there, but there's the little rule on the side. Log c to the power of x is equal to x, since in exponential form cx equals cx. So whatever number is here, okay, if the base and the answer are the same, then you will know the value for m. In B, the strongest recorded earthquake in Canada struck Haida Gwaii. I don't know if that's how you say it, but I think that's how you say it.
Haida Gwaii.
Off the coast of BC in 1949. It had a Richter rating of 8.1. How many times as great as AO was the amplitude? So we have this value 8.1. That's our m. And then we have this formula for figuring out earthquakes. So we have log A over AO. And basically all we're doing is rewriting it in exponential form. So don't forget there's nothing written here. It's a base 10 log. A base 10 log. So we get 10 to the power of 8.1 is equal to, and this is our answer, A over AO. Once you've done that, you can just isolate the A. So you'll multiply both sides by AO. 10 to the power of 8.3 AO is equal to A. And then 10 to the power of 8.1 is approximately equal to 125 million. So it was 126 rounded million times the amplitude of a standard earthquake. So really strong earthquake. The last part of this problem, compare the seismic shaking of the 1949 earthquake with that of the earthquake that struck Vancouver Island. So in this circumstance, you have the Richter values in exponential form for both earthquakes, and you're just going to compare them to see how many times bigger the Haida Gwaii earthquake was. So 10 to the power of 8.1 AO divided by 10 to the power of 7.3 times AO. Of course, these two cancel and divide out to 1. So you have 8.1 divided by 7.3 for exponents. So the Haida Gwaii earthquake was approximately 6.3 times greater. There's a couple practice problems in the practice as well as in the homework that relate to these earthquake questions. Just look through the question and see if it's similar to A, B, or C and use that to guide you on how to solve them. Beyond this, you have some practice questions that you can complete before class.
Haida Gwaii.